oil and gas pipelines. But I guess we can use the word energy if we include hydrogen and carbon dioxide and other things related to renewables nowadays. Geomorphology, well, I think I'm going to take a pretty Catholic view of what geomorphology is, but essentially it's going to be about surface processes and near-surface ground materials. So, what are geohazards? Geohazards are geological processes or conditions which can be sources of risk to pipeline operators. Here, the background photograph for this is from the southern highlands of Papua New Guinea, and you can see the sort of challenging landscapes through which many modern pipelines have had to be installed. An example of a geohazard, this is the Trans-Alaska pipeline through Alaska, obviously, and it's at the crossing of the Denali Fault. The Denali Fault is shown in as the red line is a right lateral fault. So this block of trees, can you see the cursor, Paul? Cursor works, maybe?
Yeah.
Yeah. So this side is going to be shifting to your right, and this side is going to be shifting to your left. The pipeline is unusual in this context because it's above ground, and it's above ground pipeline because of the permafrost conditions. You see the pipeline has been installed on effectively rails, and we'll see why in a second. And this is the impact of the 2002 magnitude 7.9 earthquake. What it led to was these two straight sections of pipe bowed in compression due to shortening across the fault zone. And you can also see how the pipeline has been dragged along the railings. So the risk here is obviously pipeline rupture and loss of containment of the product within the pipeline. Another big issue that dominates pipeline geohazards is river erosion and scour. And a couple of examples from both from Azerbaijan and so the diagram is showing you here how the length of the span critical to pipeline rupture is related to the flow velocity of the water. So for gently flowing streams, you might have an allowable non-rupture at 40 to 50 meters, but by the time we've got down to more extreme flow velocities, then spans of 10 meters are critical to for pipeline rupture. Landslides, obviously a big issue. Here you can see a rather large landslide at a river crossing and the resulting oil spill. This little schematic shows you, you know, where the failure modes of the landslides occur. The pipeline doesn't behave like a chain in that it would snap in the middle. It's the edges that are the critical locations where you get tension build up and buckling as well. And so this one is for a pipeline crossing a landslide, and this one would be the pipeline running down through the landslide. And here we get the complicated situation of tension at the head of the landslide and compression at the toe. One of the key issues is for how much displacement can be tolerated is related to the width of the transition zone between moving ground and stable ground. And in situations where it's very abrupt, like between bedrock and displaced soil, we can get very quite severe conditions. And where the transition zone is wider, it can be more accommodating to the strains. Here's an example of a pipeline soil interaction chart that we might be using. Along the bottom, you can see the horizontal ground movement, and the y-axis is the peak longitudinal tensile strain that can be accommodated. The normal operations, we might be looking at accommodating in the order of 4 meters, 5 meters. The pressure integrity limit is where rupture occurs. The normal operation limit might be where it's safe to operate and you can still run monitoring devices down the pipeline. The pressure integrity limit is where you can expect rupture to occur. And we're looking in terms of, for these large diameter pipeline that has been modeled here, something in the order of 5+ meters of displacement. Other situations, here we are out in the desert this time. This is an inland sabkha, a salina, and you can see all the wonderful polygonal salt heave patterns across the ground surface. Pipelines buried within this sort of environment, the groundwater is at or very close to the ground surface, and it's the interactions between the chlorides and ferrous ions within the brine with the dissolved oxygen, which leads to effectively rusting, corrosion and pitting of the pipeline. And corrosion blisters can develop within 4 to 5 years of service in this sort of environment, and it's a major driver of risk in this type of environment. And one of the things that geomorphology can add to this is the understanding between the position within the landscape, the position relative to the groundwater table, or the limit of the capillary rise above the groundwater table, and the surrounding desert terrain. So the main hazard to buried pipelines would be within saline plains or sabkha salina sort of environments. Geohazards can also be geological conditions that are sources of risk. And here's an example from Algeria, where the risk is related to not pipeline rupture, but the impact on project cost and schedule. But these poor people here were building a welded water pipeline through the desert, and it was gravity driven, so it needs to maintain a particular elevation. And they came across a buried silkrete jewelry crust, and as you can see going off into the distance, tens of rock breaking machines were required to make progress through here, and this had not been anticipated, and they virtually had to scour all the available machines in that part of Algeria to actually make progress. So here's a pipeline running through the jungle in Southeast Asia, a typical situation. The pipeline's running down the center of what's called the right-of-way, which has been cleared out of the jungle. It's revegetating, and then an incident occurs. The gully head fails, the pipeline ruptures, and we have an explosion. And you can see all of the extent of the damage around the landslide area. The operational risks to the pipeline, for the client, the operator, loss of life or injury caused by the explosion. Fortunately, no one was there at the time. Costs associated with the pipeline shutdown and repair replacement costs. Costs associated with reputational damage and the impact on their share price. costs associated with environmental cleanup and the fines imposed by host governments, and of course habitat loss as well. So there are bigger risks involved. This is, I guess all of you will remember Deepwater Horizon back in 2010, and the little chart on the left is showing you the impact that this event had on BP's share price. And the share price tumbled dramatically overnight after this, almost to the extent where BP would be taken over by other organizations. So reputational damage is a major driver in understanding and managing risk on pipelines. So what's the role of geomorphology in all of this? In fact, geomorphology is relevant at all stages of the risk assessment process, and you need to think about the contributions as effectively providing support to a global understanding of risk rather than being done in isolation. Identifying risks, analyzing risks, providing advice to identify suitable risk treatment measures, monitoring and reviewing, and communicating and consulting as well. Geomorphology is relevant at all stages of the pipeline process, from planning and design, construction, all the way through to operations. And operations typically may be in the order of 25 to 50 years. So long-term commitment to understanding these things. Oh, and on the left-hand side, here's a young man in Libya quite some time ago. What we're going to focus in this brief talk is about the planning and design stages. And I'll say a few words about construction and operation, but it's essentially we're time limited, so we'll stick with planning and design. First off, I'm going to give you a quick introduction to what actually is involved in building a pipeline through remote regions. Here we are, we're back in Papua New Guinea, and this is the vegetation clearance, the initial vegetation clearance of the proposed route. And what we're going to do is that we're going to be cutting this ridge crest down to effectively form a 3 to 4 lane working platform where all the operations can be carried out. So laying a pipeline isn't just laying it on like a hose pipe across the ground surface. There's a lot more to it than that. Same location. This is partway through the right-of-way preparation. You see the bulldozers and the spoil disposal trucks. Next comes stringing the pipeline out, and you can see the individual pipe lengths all laid out across the right-of-way into the distance. Ultimately, the pipeline's going to follow an alignment up along this ridge crest, down the base of these slopes, and down through here, avoiding all of these large landslide features that you can just pick out, and on this side as well. Next comes welding. So the individual sections of pipe are welded together. And in this photo, you can see why we need 3 to 4 lanes of width of right-of-way. Welding gear on this side, on the right-hand side, other pipeline-related equipment, and then a general lane for people who are traveling up and down the pipeline to do other sort of jobs. And if it wasn't so wide, you could imagine the holdups that would occur during the process. Trench excavation. digging the trench into which the pipeline will ultimately be placed. Typically, you're looking for it to be dug with a large excavator. In some situations, like in desert environments, the jury crust may be so strong and massive that rock breaking is required with hydraulic hammers. And in some locations, blasting is necessary as well. The welded pipe is then lowered into the ground. It's picked up by a series of side booms and lowered into the ground. And then ultimately we end up with pipeline, the reinstatement of the right of way. And it's essentially the same location. We transformed, the cleared right of way, and we're trying to get back to a situation where vegetation is re-established along this route. So, the role of geomorphology in pipeline planning and design. First, and possibly the most important, is in routing of the pipeline to begin with. And the general principle of this is the avoidance of risk. There are some places that we can't avoid, like long linear features such as faults or river systems. And then the input is related to the design of the crossings of these features with the philosophy of minimizing the risk. The risk can't be avoided. And then inputs into the design of the reinstatement measures, again, to minimize the risk of exposure of the pipeline and resulting pipeline damage. So going through landslide avoidance, so what this in essence means is that the preferred alignment for most remote region pipelines will be adopting ridge crest alignments rather than following contours, and this involves the avoidance of pre-existing landslides and landslide-prone side slopes. And it's worth pointing out that the industry experience is that major civil engineering works to stabilize large landslides are generally not practical in remote mountain areas, in part because of the impact on cost and schedule, but also the availability of suitable machinery to do the investigations. Ridgecrest pipeline. So we've been along the Ridgecrest, and now we're coming down a spur to meet a stream crossing, river crossing in the bottom. The role of the geomorphologist is essentially terrain evaluation and then field verification of that. So in this sort of example, it would be dividing the landscape up into different terrain units, each with its own characteristic package of geohazards, being out in the field, either walking through the jungle or overflights in helicopters to verify those judgments, identifying geohazards and undertaking preliminary geohazard risk assessment, including the effects of, for example, coast-seismic landslides on ridge crest alignments or spur alignments as well. Routing needs to be supported by routing, and landslide avoidance needs to be obviously supported by the base maps of the landslides in an environment. And these can be simple, effectively boundary maps. So we don't really need a lot of internal definition of landslides, just where their boundaries are and where they might retrogress to. That would be an input into the project GIS as effectively constraints which need to be avoided. There are some situations where detailed geomorphological mapping is required to demonstrate assurance that landslides have been avoided in really complex situations with multiple landslides within a valley or something similar. Sometimes the avoidance strategy is effectively isolating the pipeline from the adjacent unstable slopes, securing the integrity of the pipeline. And here you can see a line of piles being driven in along the alignment of a pipeline to separate the pipe from the unstable landslide slopes on this side. So the pipeline is going to go in just back here behind this line of piles. In other circumstances, you might be installing gabion walls or concrete block walls, again to isolate the pipe from the slope precipices on the adjacent ground. River crossing design. So the top photograph is showing you a typical river crossing, a broad gravel bed river. And the first step is actually to build a diversion channel to carry the water away from the crossing point. The pipe is strung together, welded, and then dropped into the trench, which is dug across this ponded area here. When you've done that section, the flow is diverted back down the original channel, and you do the next section of the pipeline as well. So what is important here from a geomorphological perspective, it's actually understanding the active width of the channel, the extent to which bank erosion could encroach upon the pipeline alignment, expose the pipe, and create unsupported spans, and also the assessment of the potential scour depth, which is related to the bed lowering. And the scour can be either general scour as part of the overall degradation of a channel, or it may be local scour immediately downstream of the pipeline and the protection it's got above it. So these are obviously important geomorphological inputs into crossing design. Here's an example of the sort of challenges that people might be faced with. This is a river in Turkey, and these are Google Earth images from June 2020 to March 2025, and look at the dynamic nature of the setting where they've chosen to cross the channel. Geomorphological inputs are essentially the assessment of the dynamic instability, particularly at gravel bed river crossings, and the use of scour equations for pipeline crossings. And the scour equations are basically a function of design, discharge, and the bed materials. A major issue for many crossings of gravel bed rivers is the impact of gravel winning immediately upstream or downstream, both of which ultimately generate scouring issues at the pipeline crossing. And most operators will require or prohibit gravel winning in close proximity to the pipeline, several hundreds of meters. Fault crossing design. We're looking at the crossing of the BTC pipeline in Turkey, and it's crossing the North Anatolian Fault, one of the great world's great faults. Pipeline in purple. It's another right lateral fault. So this side is going this way, this side is going that way. This is Eurasia over here, and this is Anatolia on this side. So the geological and geomorphological input into this. Firstly, we need to know what faults need design crossings. And the general principle for modern pipelines is that the assumption that faults which have been active during the Holocene have the potential to be active during the design life. And the geomorphological input is obviously identifying suitable sediments crossed by the pipeline where we can see whether the Holocene sediments have been displaced and by how much. We also need to work out the design displacements and define the geometry of the fault. And typically this will lead to a strange group of people, paleoseismic geomorphologists, down in trenches, mapping out all of the different displacements within the Holocene sediments. So I'm going to show you an example of fault crossing design. The two pictures are a gas pipeline that was ruptured in the February 2023 earthquake in southern Turkey. Again, these would be on left lateral faults. So the basic aim of fault crossing design for a strike slip fault would be to allow the pipeline here to move up and outward of the trench, and so it wouldn't develop strains which would lead to rupture or bending and buckling. And the way that this is achieved, there is a trapezoidal trench, and the trench is filled with generally granular material to allow a frictionless movement of the pipeline. The pipeline is wrapped in friction-reducing wrapping, and it lies within a trench lining. So everything is designed to allow the free movement of the pipeline during the earthquake event. Another important aspect of the geomorphologist's role is in erosion control, and most major projects define an acceptable level of soil loss, which is used then as a performance criteria to judge the quality of the work done by the contractors. And the important thing here is exposure of local damage to the pipeline are generally considered unacceptable, and there are also obviously important environmental issues associated with erosion along the pipeline. In this example, you can see a whole series of diversion berms, effectively like mini dams, collecting water across the slope and minimizing the erosion risk. And these channels are then diverting water towards a collector channel on the side. The overall aim is to ensure that the topsoil, which is reinstated, isn't stripped off, and that revegetation occurs within the next 2 or 3 years after construction. And here's another example as well. So how do we go about looking at the erosion control issue? Well, this is certainly a situation that we don't want to arise, and you can see the deep gullies which have developed on this steep ravine side slope. But basically what we're doing is using the universal soil loss equation developed for agriculture to make an estimate of the potential soil loss along the right-of-way in tons per hectare, both in the bare right-of-way situation and then trying to reduce that loss by the introduction of erosion control measures. And these erosion control measures can be factors which reduce the slope length. So you're effectively breaking up the length of the slope into a series of independent separate subunits. You're introducing crop management factors such as jute matting coverage, and erosion control practice might be effectively contour ploughing across the right of way, rather than creating the potential for rilling by scouring in an upslope downslope direction. And what we would normally do is look at how the right of way is expected to perform in response to a design storm, typically a 1-hour storm within a 10-year period. And the focus of interest is generally within the first few years before vegetation becomes re-established. Again, not what we want. The techniques that we have. Oh, sorry. Here we've got these are an indication of what are considered to be acceptable levels of erosion in the short term. Very slight, class 2, slight with minor build-up of sediment behind the berm, and moderate with the onset of some minor rilling. Where the guy standing here within this deep channel is certainly not acceptable. So what we've got in the toolkit, jute-covered diversion berms. The important thing here is that the diversion berms reduce the slope length. So the erosion potential is in part related to the length of the slope. So slope length is reduced, water is collected within the channel, and it's taken to the side of the slope. We have on steeper slopes, jute-covered terraces, jute-covered ridge crests, and at the edge of the right-of-way, cascade drain systems. So very much the responsibility of geomorphologists in helping the design of this. Another important issue in remote mountain terrain is sidecast management, and typically operators, contractors in the past would have disposed of all of the additional material that's come from cutting the ridge crest down by maybe 10 to 20 meters, would be disposing it over the side of the mountainside slope. This creates a lot of problems, not least environmental damage, but it can also trigger landslides. And you can here see a debris flow which has developed and also almost got down to the farmhouses at the bottom of the slope. So sidecast management is a really important issue in planning and design of mountain pipelines. We missed one. Right. I'll say a few words before we wrap up on construction and operations. During construction, problems occur. It's inevitable, but they need to be identified, assessed, and treatment measures installed. Problems arise during operations. Here, a debris flow has occurred, exposing the length of pipelines. Treatment measures need to be designed and installed. Sometimes there's a necessity to dig up lengths of old pipeline which cross landslides and relieve the stress within the pipe, which is what's going on here. So the stress relief, will reduce the buildup of stress, and often the pipeline will deflect back by up to a couple of meters. And of course, there's monitoring of problems, long-term monitoring. And this is the telemetry system for automatic inclinometers that have been installed in one location. Right, wrap up time. Challenges involved in the work. It's teamwork. So it's not uncommon for the client, the contractor, and the consultant all working together. So the geomorphologist is not working in isolation. He's not somebody who's writing a report, turning his back on the project and moving on. You're working with pipeline engineers, surveyors, engineer and geologists, environmental scientists, and so on. So the key skill here is in terms of communication. Communication and not hiding behind your own disciplines, jargon, and related impenetrable languages. Communication's probably the most important skill. Remote regions can be full of unexpected risks. Here, we're stuck on the mountaintop in Peru, having to be pulled out by some local cattle. Stuck in the mud in the middle of a salina in the Oman Desert. And of course, sometimes even more serious things can go wrong. And finally, it's worth stressing that major pipelines are not HS2. Project schedules are really tight, and this places significant constraints on the available time to identify and manage geohazard problem areas. This also explains why the approach to managing risk is typically risk avoidance, because although it may be potentially more expensive, it actually is easier to achieve within the timescales available. Landslides are identified and avoided rather than investigated and treated. As an example of the timescales, the pipeline in Peru that you've seen photos of, the government set a pipeline start date of 1st of August 2004, just 4 years after the award of the contract, and established a systems of fines for failure to meet the deadlines, set at $90 million if the delay was at least 90 days. So not HS2, everything is moving really quickly, and you have to be able to work in that sort of tight environment. And that's the last one. That's it, Paul.
Super. Thank you very much, Mark. Excellent pictures, really interesting to hear your experiences. Does anybody have any questions? If you can put them in the chat, I will relay those to Mark, because I'm not sure whether or not whether all of your microphones will work. Does anybody have a question? Okay, well, people are thinking. I had just a question on the monitoring. You alluded to monitoring based on that inclinometer.
Hello, Roger.
Remote inclinometer that have been installed. What's the general strategy for monitoring the effectiveness of these pipelines in remote areas? Is there technology in the pipe that can detect imminent failure, or do you just wait until a problem occurs and then remedy it?
Well, going back, the modern pipeline systems will have something like a leak detection system installed next to the pipeline. Generally, we're more concerned, or as much concerned, by anticipating problems. And so it may be anticipating the retrogression of a landslide head, and so on. So it's generally a combination of lots of different things. One of the important things is also what is called pigging, where the pipeline is a tool is run through the pipeline system, and what's called an intelligent pig will be able to map out any deflections, deformities, reduction in wall thickness of the pipeline, and pick up problems like that. Visual inspections obviously important to the ground surface, but all of these working together kind of produce the package for monitoring of a system.
Super, thank you. There's a question on the chat from Richard Jeffries. How do you account for climate change in your assessments?
I think, to be honest, it's extremely difficult, and so it is essentially another reason to be very cautious with risk. Avoidance is the main strategy, and yeah, being mindful of the fact that we don't know what the future holds.
Roger, you've got your hand up.
Yeah, hi Mark. Fantastic photographs from all around the world. It's great that you can show those. I think I know the answer to this question, but I'll ask it anyway. And that is any sort of assessment of the benefits of, say, our geomorphological routing studies ever been carried out in terms of de-risking of projects?
Okay, that you know the answer to this, but maybe you don't know the story that leads to it. In the early prior to the 1990s, the main basins which were being exploited for oil and gas were the North Sea, Gulf of Mexico, places around the US. So the experience was essentially related to offshore or relatively simple terrains. Since the early 90s, the basins have now spread to places like the Amazon Basin in Peru, Caspian Sea, central Algeria, and places like that. Places where there wasn't the experience from the engineering side of identifying and managing geohazards. And as a result, when BP first got involved in this, they identified from historical statistics of rupture frequencies that if they went ahead with conventional engineering, they would have what they considered to be unacceptable levels of risk. Now, as a result of that, Peter Fuchs was asked to lead a team of specialist geohazard experts in the design, to support the design, especially the routing of the BTC pipeline from Azerbaijan, Georgia, and Turkey. The old engineering standard might have led to, let's say, 0.3 ruptures per 1,000 kilometers per year as a general statistic. And we can proudly say that there has actually been 0 ruptures per 1,000 kilometers per year along BTC over the last 20 odd years since it's been in operation. So although you won't see it the focus of anyone's paper, the contribution of a more geohazard specialist approach has certainly delivered in those terms.
Is there any reason why that couldn't be published in some way? Because it's all about the value we bring as a discipline, isn't it? Yeah.
Point taken.
Bye.
Thanks, Roger.
Yeah.
A few more questions on the chat. So Andres Paya Garcia has said, for coastal pipelines and cables, what are the main challenges that the industry faces today?
By coastal, do we mean?
I take it to mean onshore. Yes, the landfalls.
Rather than the impact of climate change on shoreline processes, nearshore lowering, cliff recession rates, stability of dune systems, all of those things, all of which are essentially geomorphological problems. A great future for geomorphologists dealing with these issues, I think.
Thank you. And Thomas Stallman has said, do you see any major differences in the approach to managing geohazard risk for different types of cables? So he's stated high voltage electricity cables versus gas pipelines. Is there a difference in the approach for those sorts of infrastructure?
In broad terms, no. But what I would stress is the importance of understanding the vulnerability of the cable, the pipeline, or whatever you're talking about. Because, say, for example, in the case of landslides, there are some landslides, which are not going to be presenting a significant threat to a pipeline, knowing that the amount of ground displacement to rupture could well be in the order of 4 to 5 meters.
Thank you very much. A question from Ollie Burns, who makes the point that there's a tendency or a preference for nature-based solutions to manage erosion risk at rivers and at the coast in the UK, as opposed to the heavier engineering that you were talking about in terms of gabions and concrete. Do you have a view on how you overcome the inherent uncertainty in the long-term effectiveness of nature-based solutions, or would you just say, because of that uncertainty, we will not adopt them?
Yes, I think I would agree with you, because what we're effectively doing is trying to manage the risks. And say if we're talking oil and gas pipelines, then the consequences of pipeline failure and loss of containment are quite dramatic. You mentioned oil spills down rivers, gas leaks and explosions. So everything is really, really risk-driven. I know it's hard, some of you may find it hard to believe that the oil and gas industry is risk averse, but trust me, it really can be.
Thank you very much. And a final question: have you encountered any cultural or regulatory differences that significantly impacted how your geomorphological assessments were undertaken in different countries or different clients?
I don't quite know what that means.
Well, I suppose do different governments have a different attitude to risk?
Well, we're talking mainly about major oil company operators, so their attitudes would be similar across their portfolios.
And the governments who managing the countries that they run their pipelines through, will they have different policies that might conflict with or be more severe than the operators themselves?
Maybe, but not in my knowledge. I think it's useful recognizing that many of the projects are part funded by organizations like the World Bank, the International Development Bank, and so on. So they will be, let's say, imposing their own standards on the projects as a condition for releasing the funding.
Yeah, super. Okay. Well, unless there's any other questions, I propose to wrap things up. So once again, thank you very much for Mark for a really interesting set of slides that hopefully encourage people to move into that area and advertise their geomorphological skills more widely. So thanks again for your time, and thanks to you all for contributing to the discussion. Thank you.
Yeah, thanks, Paul.